we've been discussing the hydrogen atom and just sort of summarizing what we've done. It's essentially a lot of separation of variables, but we first took the Hamiltonian of our system and were able to split it into the addition of two Hamiltonians, one that only involved the center of mass coordinates and one that only involved the relative coordinates between the proton that makes the nucleus and the electron. What we did was we said, all right, we kind of assumed that the wave function of our system would be split into two parts. One, the center of mass part of the wave function, and another, the sort of relative position part of the wave function. When we did that, we had the relative Hamiltonian was written this way. We wrote it in terms of an angular momentum operator, and that gives us our relative eigenfunction, which we looked at and assumed again that it was separable into a radial part because it's spherically symmetric, and a sort of angular part. Sorry, the potential is spherically symmetric. Um, with that, we then realized that this sort of angular part is an eigenvalue of our angular momentum operator. So we did separation of variables again in the last video, and that angular part can be written as two different functions, one theta that only depends on that polar angle theta, and one phi that only depends on that azimuthal angle phi. And when we did this separation of variables, we got essentially our two differential equations. One that's just the azimuthal part, one that's a polar part. And our plan of attack essentially to get our wave function of our hydrogen atom, our eigenfunctions of our hydrogen atom, is to solve these differential equations. You know, starting with number two, we can solve this. That's what we're going to do today. It'll give us some information about this sort of separation of variables constant p that will then help us out with this one, which will solve this differential equation in the next video. That'll let us know a lot about this separation of variable constant a that will then, you know, keep going all the way up until we have our full hydrogen atom relative wave function. So let's start that, all right? This is our, sorry, a little too far there. This is the differential equation we're trying to solve. Hopefully you've seen a differential equation like this before. It's pretty straightforward. The solution to it is that azimuthal function is just going to be some constant e to the plus or minus I square root of b times that angle phi, right? And you can see this pretty quickly because if you take, you know, take one derivative, a root b comes down, I root b comes down, and take another derivative, and another I root b comes down, and we end up with negative b times the original function. This n is essentially a constant of normalization. And this b is just that constant there from separation of variables. If we sort of look at this function, you know, we can actually figure out what those variables are, right? Normalization, and so there's two things we can look at. The first one I'm going to look at is the fact that this has to be a single valued function, right? So I have some the function at some azimuthal angle. So, you know, x and y. I'm at, let's just say, let's stick to the plane. I'm at some angle phi. If I add an angle of 2 pi radians to that, I have to be at the same spot, which can only have one value. So this means phi plus, if it's evaluated at phi plus 2 pi, they have to be equal, right? And if you go through that, n e to the plus or minus I root b times phi equal to n e to the plus or minus I root b times phi plus 2 pi. The only way this is true is if e to the I 2 pi, got really sloppy handwriting there, sorry, e to the I 2 pi times root b is equal to 1, right? The only way, if for that to be true, we're essentially saying that this root b has to be equal to some integer m, right? So m can be equal to 0, 1, 2, 3, dot, dot, dot. So it has to be some integer m. The other normalization, on the other hand, if we normalize wave functions, essentially we're integrating the complex conjugate times the function over that whole angle, and we're going over all space. So once around the circle, 0 to 2 pi, this is essentially the integral of n squared, right? You take the complex conjugate of each other, those exponentials go to 1. So we integrate that over 2 pi, and we get 2 pi times n squared has to equal 1. Again, the limits are 0 to 2 pi. So we have n is equal to 1 over root 2 pi, and we're essentially done. We've sorted out our azimuthal function is equal to 1 over root 2 pi e to the plus or minus I m phi, where m is some integer 0, 1, 2, dot, dot, dot. And that's it. That's sort of the azimuthal part of our hydrogen wave function. um, excuse me, and we're essentially done. I mean, we can look at a few other things, right? One of the things, sorry, we've been using or we've discussed is that that L angular momentum operator, the Z component of it, um, operating on our wave function is an eigenvalue equation, and we can now that we have this phi, we can actually sort out what that was, right? So we've done separation of variables on our wave function enough times. We have that R function, that theta function, and this phi function. And since the position representation of our LZ operator that we've shown is, these should be partials, I H bar partial phi, partial phi, we can plug that in here, and this again only depends on that azimuthal angle, so both of these functions can just come to the other side. We have our theta IH bar partial phi acting on our function 1 over root 2 pi e to the plus or minus I m phi. This gives us, we have I H bar R theta, oops, sorry, should pay a bit more attention. R theta of theta times the derivative of this is just going to be 1 over root 2 pi plus or minus I times m e to the plus or minus I m phi. This whole thing ends up being negative plus or minus, negative minus or plus, sorry, negative plus h bar m times r theta of theta and phi of phi, right? So we've just derived what the eigenvalues of that LZ operator are. Right? If we operate LZ on our wave function, we get the eigenvalues m plus or minus or plus h bar m, which was the eigenvalue equation we've sort of assumed or been using for a while now, where if we have some LZ operator acting on some eigenstate that's characterized by this quantum number m, we just get m h bar times that m, which is our eigenvalue equation. So we've finally now derived that eigenvalue equation in our position representation, and we have the position, sorry, the wave function for that LZ eigenstate. One final thing we can sort of do to help us get a handle on how this affects the energies in our hydrogen atom is we can look at a simplified system here of essentially a particle confined to move around a ring at some angular velocity omega, say, right? If we look at this situation where we have, sorry, that particle confined to plane moving around a ring, we can think about the energy of that and sort of use this wave function, I guess, to describe it, right? We have energy eigenvalue equation for a system like this would look like that, right? And the Hamiltonian in this situation, it would just be the kinetic energy, right? So the kinetic energy is 1/2 mv squared, or if we're looking at rotational kinetic energy, some object going around in a circle like that, it's just going to be 1/2 I omega squared. Or if we wrote this in terms of angular momentum, it would be that z component of angular momentum squared divided by 2 times the moment of inertia, right? Because this is going around, if this is our x and y axes, z would be coming out of the page. And if we look at the vector description of that rotational motion, the angular momentum would be pointing in the z direction. And it would just be the moment of inertia about that z-axis, I omega, right? Classically, we'd be looking at that where these are both the z components. So we have that, and we can sort of think about this. We've just described, if we were looking at quantum mechanically, this LZ operator. We just derived the eigenfunctions and everything for that. So if we wanted this Hamiltonian LZ squared over 2I, if we were to operate that on our wave function, this is just going to be m squared h bar squared over 2I times that wave function, where this wave function, again, we've sort of made up this sort of fictitious, system just to kind of explain this, that is essentially the hydrogen atom where all there is that azimuthal part. So we've got that, and essentially we've shown that the energy for this system would be m squared h bar squared over 2 times the moment of inertia. And one of the things you can note here is there's a degeneracy here, right? M is an integer, 0, plus or minus 1, plus or minus 2, etc. So, given, if I gave you an energy, you can narrow it down to 2 of these values, but you don't know which. This is essentially, the fact that if the particle is moving, counterclockwise with some omega, it has the same energy as if it was moving clockwise with some omega. So the azimuthal, essentially what we've shown is that these azimuthal eigenstates that we've derived are energy eigenstates as well, right? We, essentially, not essentially, the Hamiltonian commutes with our LZ operator. So they share eigenstates. We've just derived today that these azimuthal functions, this 1 over root 2 pi e to the I m phi, that these are eigenstates of the LZ operator. Turns out they're also eigenstates of the Hamiltonian operator. But there is a degeneracy in the energy eigenvalue for that. So yeah, just a quick summary. This video is relatively short. We've shown that the eigenstates for the LZ operator in position representation are these functions we just derived: 1 over root 2 pi e to the I m phi, with m equal to 0, plus or minus 1, or plus or minus 2, some integer, and that it is, the eigenfunction of our LZ operator, and it is also an eigenfunction of our Hamiltonian. It's a simultaneous eigenfunction. So that's that. Next video, we are going to use this and then look back and look at the polar part of that wave function.